So what does all of that have to do with chemistry? Well, when atoms or molecules absorb energy, they will often release that energy later in the form of light. And examples of this are fireworks and neon lights. So here's a picture of fireworks, and here's a neon light. Do you know how a neon light works? It actually has neon in it. It's a gas tube. It's not heated, it's got an electric voltage passing through it. So basically you're zapping it with electricity, which is giving it energy. It accepts the energy and then it gives it back as light. And each element has its characteristic color. This is the characteristic color of neon. A true neon light is always this bright reddish orange. If you've got some other color, it's either another element or they've used some special glass or something, but that's what neon does. This is what mercury would look like. This is helium, and this is hydrogen. So if we take light from an excited element like this and pass it through a prism, we don't see a whole rainbow like we do with sunlight. We see some lines, and the lines have different colors, but it's not a continuous spectrum. It's called an emission spectrum because this is light that's emitted from these elements. And so it will have bright lines at particular wavelengths, and those will be the same for that element no matter when or where or how you do it. And so it can be used like a fingerprint or a barcode to identify a particular element. And this phenomenon cannot be explained by classical physics. So here's what happens. So here we have a hydrogen lamp. There's hydrogen gas in there. We're zapping it with electricity, and it's giving off this kind of pinkish light. We pass that through a slit so that we don't get too much of it, and then we pass it through a prism, which breaks the light into a rainbow. If this was sunlight, we would see a continuous rainbow down here, like this one. But for hydrogen, all we see are 3 little lines, and in between is darkness. If you do this with helium, you see more lines. This is barium, oxygen, and neon. Neon's got a lot of red, orange, yellow lights up here. That's why the light appears that color. It does also have some blue light that it emits. But yes, this is how a gas spectrometer works. So if you notice, this orange line here is in the same area as the orange lines for barium, because the wavelength for orange is in this region. And so the lines, each of these lines has a specific wavelength of light, which corresponds to a particular energy. So we can look at absorption or emission. So this is emission for mercury. This is the light that it gives off. But we can also do the opposite and take a sample of mercury gas and shine bright light through it and then see where it absorbs the light. And then you see dark lines instead. And this is the basis of atomic spectroscopy, where you're measuring the light that's absorbed or emitted by the element. Flame tests are very old way of identifying elements, where you dip this piece of wire into a solution of sodium chloride, and then you stick it in a flame, and you'll get this bright yellow flame. Sodium is all over the place, and so you see that bright orange flame a lot. Potassium, lithium, barium, it's kind of hard to see, but that's kind of a greenish light. And so the colors that we're seeing coming out of them is our eyes are taking all the different lines that they emit, and combining them together into one color, right? We perceive a single color. We don't see lines. We see it as a color. So this was all very interesting. Rydberg analyzed a lot of different atomic spectra, and he's trying to figure out some mathematical relationship between the lines. And he came up with the Rydberg equation. So 1 over the wavelength is equal to a constant times the quantity 1 over m squared minus 1 over n squared. M and n are just integers. 1, 2, 3, 17, whatever. So putting different integers in here would give you wavelengths that were observed in various atomic spectra. So this is nice, but it doesn't really do much. It doesn't tell us why any of this is happening. Why are atomic spectra discrete? Why do they have specific lines? Why are atoms stable? Why does the equation work? We don't even know that. So it's kind of a nice start, but yeah, we need a little bit more. So if we think back to Rutherford's nuclear model of the atom, this came out of the plum pudding or blueberry muffin model, which was found to be incorrect. So the nuclear model, we've got a nucleus in the center. This is tiny and extremely dense. Almost all the mass of the atom is in that nucleus. The nucleus is positively charged, and then we have electrons around it doing something, moving around in empty space. The charge on the electrons is equal to the charge on the nucleus. Okay, a review, nuclear model of the atom. Well, electrons are charged particles and they're moving. And classical physics says that moving charged particles give off energy. So electrons must be releasing energy. Why don't atoms glow? And why don't they collapse? If the electron's losing energy, isn't it going to run out of energy? And then it'll get sucked into the nucleus and the whole atom would collapse. But that doesn't happen. Classical physics just doesn't help us much here. And this nuclear model also doesn't tell us what's going on structurally when atoms gain or lose energy. So enter the Bohr model of the atom. Niels Bohr, this is the same guy from the quote at the beginning of the chapter. Anybody who's not shocked by quantum mechanics doesn't understand it. So he developed a model to help us figure out what happens with these energy transitions. And what I like about the Bohr model is it's easy to visualize. It's relatively simple. It's nice to think about. The problem is it's wrong, but it works for hydrogen. It works for one of the elements, so that's great, but not so useful. It's still a useful model, though. So in this model, it's a lot like the solar system, where the sun is the nucleus, and the planets are the electrons. And the electrons are going around the nucleus like planets around the sun in these orbits, right? It's easy for us to think about that. The orbits exist only at specific fixed distances from the nucleus. The Earth has its particular orbit. You couldn't just move it in a little bit or move it out a little bit and have it at a different distance. That wouldn't work, right? There's only the specific distances. The energy of the orbit is fixed or quantized, and the amount of energy in the atom is related to the electron's position in the atom. So what does quantized mean? Quantized means that your only specific values are allowed. So if we think about our monetary system, we have coins and we have bills. There's a penny, a nickel, a dime, a quarter. We won't go into the more obscure ones. There's $1 bills, there's actually $2 bills, 5, 10, 20, right? Ever seen a $17 bill? No, they don't exist. Why? Well, they just don't, right? you're either the $10 bill or the $20 bill. Now you could combine some smaller things to make 17, but there's nothing in between, right? So for these orbits, they're like the coins, right? They have a fixed value. There's the penny and the nickel and the dime and the quarter. And there's nothing in between. We can also think of quantized in terms of stairs. So, you're going up the stairs. You can stand on this step or this step. You can't be partway between. Or if we think about a ladder, right? There's rungs. You're standing on one rung or the next rung. You can't be in between. So those are both quantized things. Continuous would be something like a ramp. So on the ramp, you could be down here. You could scooch up just a smidge. You could be at any distance above the ground. Anything's possible. The ladder and the stairs, that's not true. There's only particular levels that you can be at. Anybody have any questions about that? So this is a sketch of Bohr's model. Here's the nucleus, like the sun, and then we have these orbits that are possible for the different electrons. So orbits that are closer to the nucleus are lower in energy, and orbits that are farther from the nucleus are higher in energy. And what Bohr proposed was that when we see emitted radiation, such as this 434 nanometer light that we observe, that corresponds to a transition of this electron from the fifth orbit to the second orbit. And this blue-green with a longer wavelength, less energy, corresponds to a transition from n equals 4 to n equals 2. And this is even lower in energy, and so this is a smaller transition. So when the atom absorbs energy, the electrons can be moved up to a higher energy level, a higher energy orbit. It's not stable, and it'll fall back down eventually, and when it does, it releases that energy as a packet of light, a photon of light. And the energy of the light corresponds to the energy difference between those two different orbits. What's really kind of freaky is that an electron is never between orbits. It's either in the fifth orbit or it's in the second. It doesn't go in between. It's called a quantum leap. It's a leap from one quantized state to another without going through anything in between, because nothing in between is possible. Have you heard of the TV show Quantum Leap? They had a long series back in the 80s, and now they're making a new version. I saw the first one. It was pretty good. So this guy makes these quantum leaps, right? He's here, and then he goes through space and time, but he's not actually traveling through space and time. He's just suddenly in another person's body at a different time. And it's not like he is flying through the air, right? He's there, and then he's over there without passing in between. That's what electrons do. It's kind of hard to understand. So the energy of the photon that's emitted is the difference in energy between those two states. We can calculate the energies because we can measure the wavelengths. So this was a huge historical development, and it's very important conceptually, but unfortunately it only works if you have one electron, and that's only hydrogen.